let's consider that a plate is lying in the xy plane. The z is the out of plane direction. We consider a thin plate over here. I'm just going to draw a certain element of it so I can show you the loads that are acting on it. The membrane forces that are acting on this per unit length, for example, can be given as Nx, Ny, and of course there is a shear which will be given as Nxy. You have to find out the geometric stiffness matrix, which can be obtained by the work done by the constant membrane forces as they are acting through this element. So to find out the work done by the constant membrane forces, we need to find out the membrane energy or the membrane strain energy. We also therefore need to find out the membrane strains which the element is undergoing at this point. If the displacements that are occurring in the out of plane direction z is given as W, then we can write the associated membrane strains to be epsilon x is given as half of dou W dou x square, epsilon y is given as half of dou W dou y square, and the same way gamma xy is given as dou W dou x and dou W dou y. So this is the description of the membrane strains. Now the change in the membrane strain energy associated with these membrane forces, which are assumed to be constant, can be written such as the membrane strain is given as an integral of half of the load which is acting in the x direction times the epsilon xx. So it's not half of that, but then the load times the displacement over here. So you have dou W dou x square plus half of ny dou W dw dy square plus nxy dw dx dw dy. And all of this has to be integrated over the area right here of the element. I can also write this in a vectorial and matrix format, where I would have half of a double integral, so I can get the half out from this equation, half of the double integral of, instead of writing dw dx, I'm going to write it as w dash of x and w dash of y times the load that is acting, so nx, nxy, nxy, ny, times, so this is transpose, times w dash x and w dash y. Now the area can be decomposed into both the lengths x and y, so I write dx dy, and in an even simplified manner I can write it as half of the total displacement. So if I say w transpose, I shouldn't write here w, I'll use u because that's the displacement I've been using for the entire element, so u transpose k g u. So going by this definition, let me continue on the next page. Going by this definition, we have the u is equal to, or the w in that case is equal to the n times u. So u dashed is equal to g times u. This is element g times u, which is n dx. Therefore, putting everything back into the main equation, you would be left behind the same way as before, as kg is a double integral of g transpose times the load matrix for the components and g dx dy, which is over the lengths x and y. If the element is of course of an isoparametric family, then you can make it into the generalized coordinates psi and eta. You need to get a Jacobian matrix in that case, and your limits move from x, y to psi and eta. I don't want to confuse you with it, but just for the sake of completion, I can also write this as -1 to +1 for both the integrals, g For isoparametric elements, transpose Jacobian inverse transpose times the load matrix carried forward from before times the Jacobian inverse G for isoparametric elements times the Jacobian d psi d eta for generalized coordinates. This is a standard formulation for a plate element. So if you think about it carefully, then we have been following the same general description for the kg for each of the element. It includes the derivative with respect to length or area of the shape functions, along with the description of the load in between. So either it can be the membrane loads, which are nx, nxy, and ny, or it can be the simple load which is acting in tension, for example, in the bar, which was given as P. So in a generalized formulation where we can work with stresses and strains, we can also describe the geometric stiffness matrix in the way that we did in the previous lecture. So we can say that under a certain small strain condition, you can have engineering stress that may be defined. So we can write the the work done, the virtual work done associated with the strains to be equal to the strain times the stress, which is integrated over the entire volume given over here. Of course, your sigma naught refers now to your engineering strain, but if you need, you can also use the pk strain as and when required. So if we want to write the energy which is associated with the geometric stiffness, then we can expand this for a three-dimensional case where you have the u, v, and w acting in 3 dimensions as the different displacements. So if I put that all together, I get a very large equation. I will just compress it over here in the form that I can have du dx square plus dv dy square plus dw dz square times the stress acting along x naught. Then I will have similar terms with stress acting along y naught and so on, and also with the shear stresses. All this needs to be multiplied with the dv because it's being integrated over the entire volume. Now if we say that we have a certain displacement vector which is given as du dx, let me write it, dv dy dw dz, and in the same way for all the different terms. So if I'm going to only use, sorry, I should write this in the correct way. If I have du dy dz, and in the same way I continue with dou v, dou x, dou dv, dy, and so on for all the 3 u, v, w with respect to x, y, and z, then I can write now the energy to be equal to half of integral of this displacement vector with the derivative of the displacement transpose times the stress vector for the 3-dimensional case. This is of course a tensor times the displacement with the derivative of the displacement times dv. This expression is analogous to the previous terms that you have been using, like this was related to G transpose, this was related to G by means of the degrees of freedom. So if I substitute that, then I would be able to get half of the integral of U transpose G transpose with S tensor with G and U dv. So in the end we get the kg to be equal to the integral of G transpose S G dv, as we have been doing in the cases for individual elements. Just giving you a flavor of how the geometric stiffness is formed. This of course applies to both linear and non-linear buckling problems. or anything that relates to geometric stiffness in the end. So it's always good to know where the terms are coming from and how they are used to describe the changes that are happening because of the load in the system and not just the material properties.